Hello and welcome back to Anton Math. Now in this video we're going to be doing some more problems with our selection and permutation functions. So let's go ahead and dive in. We've got 4 examples here in this video. So the student council consists of 6 juniors and 12 seniors. A committee of 2 juniors and 3 seniors is to be formed. How many ways can this be done? Now we're going to be incorporating the multiplication principle in here. So first we want to look at how many ways there are to choose the juniors. There's 6 total juniors, and we need 2 juniors for our committee. So there's going to be 6 choose 2 ways to choose our juniors. Right? We're using the choice function here because our order doesn't matter. It doesn't matter in which order I choose 2 juniors. If I choose junior A and junior B, or junior B then junior A, I've still chosen the same 2 juniors. So that's what's important in this problem, right? This is not an order problem. Now, for each of these choices of juniors, I'm going to have how many choices of seniors? Well, there's 12 seniors. I need 3 of them. So that's going to be, there's 12 choose 3 total ways for me to choose 3 seniors from the group of 12. Now we multiply here, again, just to review a little bit, we're multiplying here because for every choice of juniors, I have 12 choose 3 seniors. So I need to multiply how many choices I have of juniors by how many choices I have of seniors to get the total number of choices of the combination of the 2 that I have. Now I'm going to work this first one out in detail. For some of the other examples, I'm just going to formulate the solution and then give a numerical answer. And I encourage you to work out on paper with a calculator using Wolfram Alpha, work out my formulation on your own to get to that numerical answer. But we'll do this first one together. So 6 choose 2. I know that that's going to be 6 factorial divided by 2 factorial times 6 minus 2 factorial, which is just 4 factorial. And 12 choose 3, that's 12 factorial, divided by 3 factorial, times 12 minus 3, or 9 factorial. Now I can simplify this down. 6 factorial divided by 5 factorial is going to be 6 times 5, right? The reason being, it's fairly clear, but 6 factorial is just 6 times 5 times 4 times 3 times 2 times 1, or in other words, is 6 times 5 times 4 factorial. So this is 6 times 5 times 4 factorial, which cancels with the other 4 factorial. And over here I can do something similar. This is going to be 12 times 11 times 10 divided by 3 factorial. Well, 2 factorial is 2 times 1, so that's just 2. So I'm going to have 6 times 5 divided by 2, which is the same as 3 times 5, or 15. And over here, 3 factorial is 3 times 2 times 1, which is just 6. So which is just 6. So 12 divided by 6 is 2. I'm going to get 2 times 11 times 10. Well, 2 times 10 is 20. 20 times 11 is 220. Let's document that right here. 220. And 15 times 220 is 3,300. So there are 3,300 different ways to form this committee from this 18-person student council. Okay, so we worked that one out together. So in these next ones I'm going to formulate it and I'll give you the numerical solution, but I encourage you to work it out, those intermediary steps like we just did. Now for this one, we'll break this up into 2 parts. Part A says, how many 12-bit binary strings with 5 ones are possible? So now a 12-bit binary string, that's going to be a string of zeros and ones, right? Where there's 12 total, so let's see here, 4, 8. So this is an example of a 12-bit binary string with 5 ones. Okay? So how many of these are possible? How many ways can we have these 12-bit binary strings with 5 ones? Well, if we think of each one as being me choosing one of those objects to be a 1, then I have 12 different objects, and for every different 5 of those objects that I choose, I have a different string of binary with 5 ones. So this is just going to be 12 choose 5. Right? I have 12 different bits in my binary string, and I want to see how many ways I can choose only 5 and exactly 5 of those to be 1s. So that's exactly 12 choose 5, which is 792. Again, I'll let you work that out. Now for part B, how many of them start with 101? So now I'm looking at binary strings 1, 0, 1, and then I have 9 other bits. And I'm still looking at a total number of 5 ones. So this problem basically boils down to now how many ways can I take these 9 bits and make 9-bit binary strings that contain 3 ones, right? I already have 2 of my ones over here, so in these 9 bits there's going to be 3 additional ones. So that's just 9 choose 3, the same way that we did part A, right? And that's going to be 84. So 84 of these 792 12-bit strings have 101 for the first 3 bits. All right. Get a little harder. Now, a club with 24 members wants to elect a committee consisting of president, secretary, and 3 ordinary members. How many committees are possible? Now, in this example, I'm going to do this one a couple of different ways so that we see that there's usually not one way to attack one of these problems. So first I'm going to use our multiplication principle, and let's say I want to choose the president first. So if I choose the president first, that's 24 choose 1. Right? This is how many ways I have to choose the president. There are 24 members. I can choose the president in 24 choose 1 ways. Now, after I've chosen the president, or in other words, for every choice of the president, there's going to be 23 choose 1 choices for the secretary, right? I've already chosen the president now, so there's only 23 members remaining. So of those 23 members, there are this many ways to choose the secretary. Now, I don't want you to get confused. This doesn't mean that I've already chosen one president and there's 23. This means that for every one of my choices of president, no matter which person I chose for president, this is how many ways there are now to choose the secretary afterwards. And after I've chosen the president and the secretary, there's 22 choose 3 ways for me to choose the 3 ordinary committee members. Now 24 choose 1 is just 24. 23 choose 1 is just 23. Oops. And 22 choose 3 is 22 factorial over 3 factorial. 22 minus 3 factorial, which is 19 factorial. I could write this as 24 factorial. Right, I can multiply this 23 and 24 over 3 factorial, 19 factorial. And I'm just doing this so that we can compare our other methods, make sure they're the same. And this is going to give us a total of 850,080 ways to choose this committee. Now let's just say that we attacked this problem in a different way. Let's say instead I'm like, well, I want to choose my ordinary members first. Well, if I choose my 3 ordinary members first, there's 24 choose 3 ways to do that. Afterwards, there's 21 choose 1 ways to choose either my president or secretary, doesn't matter. And then after that, there's 20 choose 1 ways for me to choose the president or secretary, depending on what I chose first. Now I just want to try to make it match one of these things I have up here so we can make sure that this is actually going to be the same. So this is 24 factorial over 3 factorial, 21 factorial, times 21 times 20. Now this 21 and 20 are present in this 21 factorial, right? 21 factorial is 21 times 20 times 19 factorial. So this 21 and 20 cancel with this 21 factorial, and I just have a 19 factorial in my denominator. So this is just 24 factorial over 3 factorial, 19 factorial. So it doesn't matter if I choose the president first, the secretary first, the 3 ordinary members first. This multiplication principle is going to give us the same result. Now let's say I wanted to use permutations instead. And what I mean is, let's say that we choose the entire committee at once. So there's 24 choose 5 ways for me to choose 5 people out of the 24 members. So these are going to be the 5 members of my committee. Now I still have not assigned president or secretary. So what we're going to do is, for every choice of 5 people, I can either do 5 choose 1 for the president and 4 choose 1 for the secretary, and just continue on with our multiplication principle. Or I can multiply this by p 5 2. Right? So what I'm saying is, once I've chosen the 5 people to be in my committee, I want to look at how many permutations there are from that committee of 5 people, where each permutation is of size 2. Now in this permutation, we would just say the first value in the permutation is the president, and the second one's the secretary. So then if you flip them, it's a different permutation, and it means something different in our problem. So let's just make sure this works out for us. This is 24 factorial over 5 factorial, 19 factorial. And P52, I know that that's just 5 factorial over 5 minus 2, which is just 3 factorial. And we see almost immediately our 5 factorials cancel, and we get 24 factorial over 3 factorial, 19 factorial. So no matter which of these ways that we use to attack the problem, and the other one that I talked about just now and didn't say was that we can choose our committee of 5, and then choose our one president from those 5, and then choose our one secretary from those 5. And that's just going to be the same. Right? We're going to get this exact same arrangement up here. But no matter which of these ways that we attack the problem, they're all equivalent. So there's not one right way or a wrong way to do it. I mean, there's lots of wrong ways to do it if you miscount, but there's not always one right way to count it. So if you don't have the same method as somebody else that you know, that doesn't mean that you're wrong necessarily. Work it out, check the answer, and as long as your reasoning for coming up with that solution is correct, you should have the same numerical answer as anyone else. All right, one last problem. This is dealing with cards. These are very popular problems when we talk about counting. So a regular deck of cards contains 52 cards, 13 spades, 13 hearts, 13 diamonds, and 13 clubs. A 5-card hand is dealt. So I don't know how many hands contain only spades. Now, a lot of people would be scared of this problem because they see 52 cards and start doing things with 52 cards, but I'm not concerned with all 52 cards in this problem. I just want to know how many hands contain only spades. In other words, if I look at my spades, how many ways can I choose 5 spades? Well, I only have 13 spades. And I want to look at how many ways I can choose 5 of them. So that's going to be 13 choose 5, which is 1287. Right? I'm not concerned with all 52 cards because I don't care about a 5-card hand that has 4 spades and 1 heart, or a 5-card hand that has no spades at all. I just want to know how many 5-card hands are possible that are all spades. So I only need to look at my 13 spades. Now for the second part, how many hands contain 3 spades and 2 clubs? Well, I know that there are 13 choose 3 ways for me to choose 3 spades. And for every one of these choices, I can make a hand of 5 cards with any 2 clubs. And there's 13 choose 2 ways for me to choose those 2 clubs. So, working this out, this is one that you can work out on your own. There's going to be 22,308 ways for you to deal a 5-card hand that has 3 spades and 2 clubs. Now for this last part, we need to break this part up a little bit so it looks a little bit more like part 2. So part 3 says how many hands contain only spades and clubs, at least 1 of each. So anywhere from 1 to 4 of each. Well, breaking this down into the scenarios that match part 2, I know that there's going to be 13 choose 1 times 13 choose 4 hands that contain 1 spade and 4 clubs. There's going to be 13 choose 2 times 13 choose 3 hands that contain 2 spades and 3 clubs. 13 choose 3 times 13 choose 2 hands that contain 3 spades and 2 clubs. And 13 choose 4 13 choose 1 hands that contain 4 spades and 2 clubs. And that's going to give us a total, after you work that out, of 63,206 possible hands with spades and clubs where there's at least 1 spade and 1 club. Now we could do this a different way. We could instead say, well, I'm going to take all of my spades and clubs, there's 26 of those, and I want to look at how many ways I can deal a 5-card hand from all of those spades and clubs. So there's 26 choose 5 possible hands that consist of spades and clubs. Now we're not done yet because this also includes all of those hands that are entirely spades or entirely clubs. So what I need to do is I need to subtract from this how many possible hands I have that contain only spades, and I need to subtract the amount of possible hands that I have that contain only clubs, right? Or in other words, 26 choose 5 minus 2 times 13 choose 5. I'll let you work that out on your own. You should get the exact same number here as you got from there. So just like in the last example, as long as your formulation of what the problem is asking is correct, there are more than one way, there's many ways often, in which to solve these counting problems. Alright, this was a little long. I hope these examples were helpful. Now in the next section we're going to be talking about the binomial theorem and its correspondence to these counting problems that we've been doing so far. We'll see you there.